Hey guys, we are jumping into our next unit, which is stoichiometry. I really like stoichiometry. It's very mathy, and most students during stoichiometry, they don't really like it. They think it's hard. But when you look back on chemistry at the end of the year or next year, students always come back and be like, oh, I really liked stoichiometry. That was one of my favorite units. And I was like, at the time you hated it. And they're like, no, that's easy. So hopefully you'll feel that way towards the end of it or when you look back on it with stoichiometry. Also, I want to just say you all are doing a really fantastic job. I know virtual learning is not fun and it's not easy, but so many of you all are showing up every day. You're watching the videos, you're doing the assignments, and you're really getting it, and honestly getting it better than I thought that you would. Be able to in a remote setting. So I don't say that to say anything negative about you all, but actually just to pat you on the back and say thanks for continuing to work at it every day and, emailing if you have questions and just being wonderful and awesome in despite of the pandemic. So let's move on. I usually kind of skip over the bell ringers when I do this virtually. They're always embedded in the PowerPoint, but I kind of skip them. But I want to do this one today because it's going to kind of help us get into stoichiometry. So if you were in the classroom, I would just ask you to work this problem and just let you do it however you want to do it. So let's read through it together. Silk is one of the most luxurious of all the fabrics. It's spun from cocoons of tiny silkworms, which transform the leaf of mulberry trees into silk thread, which they use to weave their cocoons. More than 3,000 cocoons are needed to produce enough silk just to make one Japanese kimono. How many cocoons would be required to make 5 Japanese kimonos? So you would probably say, well, if it takes 3,000 to make one and we're wanting to make 5, it's going to take 5 times 3,000 or 15,000 kimonos to make, or 15,000 cocoons, to make 5 kimonos. Okay? And that would be right and perfect. Okay? But the way that I really want you to start seeing things and setting things up always when we do stoichiometry is in dimensional analysis fashion, where we say that it takes, we're trying to make 5 kimonos, and we know that one kimono takes 3,000 cocoons. And so therefore 5 times 3,000 is going to be 15,000 per one kimono. Okay, and we set that up in a way where our units would cross out. Okay, so this is really, really important. Part of your assignment today is to go back and practice some dimensional analysis because it's going to be, stoichiometry is very heavy in this type of problem. Okay, so you'll have some essentially kimono homework, not based on all kimonos though. So I want you to just remember this though and recall this as we move forth. So what is stoichiometry? Stoichiometry is the calculation of quantities in chemical reactions. So everything that we've been talking about so far is dealing with moles and atoms and grams. But we want to actually know in chemical reactions, if you put in X number of grams of one substance and are trying to make a new substance, what is that ratio and how does that work out? And so that's what stoichiometry allows us to do. So let's look at this chemical equation together. The first thing that you will notice about this chemical equation is that it's balanced. And that's really important, okay? Always in stoichiometry, when you start, you want your equation to be balanced. It has to be balanced to be able to work with it, okay? Because that shows you the proportion of elements that are formed. For example, it takes 1 nitrogen to be able to make 2 NH3s, which is an ammonia. It takes 3 hydrogen, 3 moles of hydrogen to make 2 NH3s, okay? And that's really important, okay? So let's look at this. What I'm asking you to find here is how many atoms are present, how many molecules, moles, the mass, and then the volume. So I'm going to kind of work through these a little bit out of order, okay? So bear with me here. So moles. We find moles by looking at the coefficient, okay? Moles is found by looking at the coefficient. And so the coefficient here, we have 1 mole of N2. We have 3 moles of H2. And we have 2 moles of NH3, okay? That is the mole ratio, all right? Now let's look at mass. Mass, we have to calculate by looking at the mass on the periodic table, okay? So the mass of nitrogen is 14. So N2, the mass there is going to be 28 grams. 3H2, H is 1 on the periodic table, and we have 6 essentially of those. So it would be 6 grams. And then 2NH3 over here. So we've got 2 N's again, so that's 14 and 14 makes 28 plus 6 more H's. And so that should be 2NH3, if you add all of those up, would be 34 grams, okay? So you can just find the mass of NH3, 14 plus 1 plus 1 plus 1, all 3 of those. And then you can multiply that by 2. So that's 17 times 2 gave me the 34, okay? Or you can look at it as 2 nitrogens and 6 hydrogens and add it up that way. It's the same either way. What I want you to see here, though, is if you add up the reactants, 28 plus 6 is 34. That matches the mass of the products, okay? In a chemical reaction, mass is always conserved. It's always conserved. This is called the law of conservation of mass. In a chemical reaction, mass is always conserved. Okay. Another thing that's conserved in a chemical reaction is the number of atoms. Okay. So you know how to do this from when we balanced equations. Remember, you would write N and H, and you'd count the N's on the left and the H's on the left, and you'd count the N's on the right and the H's on the right, and you would say that it's balanced. So here we would say there are 2 atoms of nitrogen and 6 atoms of hydrogen on each side of the equation, okay? And that's important there. Now, molecules, remember from stoichiometry when we did it before, 1 mole is equal to 6.022 times 10 to the 23rd molecules, or you could even say atoms if you want to call it atoms too. That would be the same thing, fine. So you can sub that in there. It doesn't really matter to me, honestly. 1 mole is 6.022 times 10 to the 23rd molecules or atoms. So when we're counting molecules here, it would be, we have 1 mole. So we're going to have 6.022 times 10 to the 23rd molecules of N2, okay? For H2, right here, we have 3 moles. So it's going to be 3 times 6.022 times 10 to the 23rd molecules, which would be 18.066, I think, if my math's good, okay? Times 10 to the 23rd molecules. And then for NH3, again, it's going to be 2 times, whoops, I got on the wrong line, sorry. 2 times 6.022 times 10 to the 23rd molecules of NH3. Or if you wanted to multiply that out, you could say it's 12.044 times 10 to the 23rd molecules of NH3. Okay? And honestly, you could do the same thing on this for the atoms. You can count your atoms like this. That's how I usually do. But realize that truly those numbers times 6.022 times 10 to the 23rd atoms. Okay. And then lastly, let's look at volume. So if you remember before in volume, 1 mole is 22.4 liters. And that's for gases. So all of these are gases. Okay. So we have 1 mole of nitrogen. So that would be 22.4. Okay. Liters of nitrogen. We have 3 moles of hydrogen. So that would be 3 times 22.4 liters of hydrogen. Okay. And then we have 2 moles of NH3. So that would be 2 times 22.4 liters of NH3. Okay. And you could multiply those out if you wanted to. I just don't have a calculator here handy to do that. I would actually prefer that you do, though. Okay. So this one would be 44.8 liters of NH3. And this one would be 67.12, if my head math is good, liters of H2. Okay. So that is how you work through these problems. So I want you to look at these, and I want you to tell me if these problems are, if these basically are balanced or imbalanced, if they are correct or incorrect. So the first one you should say is written incorrectly. It is not balanced. H3 plus 1 more H there makes 4 H's, and over here there's only 2. Okay? So you may be able to go in and balance this, but the way it's written is incorrect. Okay? If you look at the second one, you should say that it's written correctly, and it's ready to do stoichiometry with. Okay? You have 2 H's and 2 I's, 2 H's and 2 I's. Okay? Now, what about this last one? It's a little bit trickier. This last one you should say is written incorrect. Okay, this is not a correct chemical equation. And the reason you should know this is that it does not obey the law of conservation of mass. 2 grams is not going to break down into 2 grams and 1 grams because that doesn't mean that the mass was conserved like we talked about. Okay, so that is incorrect. So let's do another practice here. Again, this is another one similar to the kimono where we want to set up and try to do dimensional analysis to solve a problem. So this is kind of like a chemical equation, right? It's got these letters, which are elements. It's got these coefficients here. And it doesn't really make a whole lot of sense, but these all stand for different things. So I want you to try this along with me. In a 5-day work week, Tiny Tyke is scheduled to make 640 tricycles. Okay, how many wheels should be in the plant on Monday morning in order to make these tricycles? So we have to start with what we're trying to get. So we are trying to get, the problem gives us 640 tricycles. Okay, so to make 1 tricycle, here is our equation to make 1 tricycle. F is a frame, so it needs 1 frame. S is a seat, it needs 1 seat. It needs 3 wheels, which is the W. It needs 1 set of handlebars. It needs 2 pedals, and that makes this, which is our whole tricycle. Okay, so we're trying to make 640 tricycles, or more specifically, we should call it 640 FSW3HP. Okay, that's what we're wanting to make. So in order to make 1 FSW3HP, okay, that's what all these are, 3 wheels, 2 pedals, as shown in our equation. That's a combination reaction there for you. To make 1, the question is how many wheels should be in the plant on Monday morning? So one tricycle, FSW3HP2, requires 3 wheels, okay? So in order to solve this equation, we can cross this out, and we'll multiply 640 times 3, which is going to be 1,920. Okay? 1,920 wheels is how many you need in the factory on Monday morning to make the tricycles. All right? So that's kind of a little bit of a chemistry application to this. So now here's one for you to try. You can push pause on me, and you can try this on your own, and I'm going to work it out here. So calculate the number of each item needed for 45 packages. So I calculated 45T, 135W, 45M, 90C, and 180L. And I know you're thinking, man, Miss Brown, that's a lot of work. Why did you write all of that out? Trust the process, guys, okay? Yes, I know that you could have just multiplied by the coefficients and said you're going to take, it's just going to need 1 times 45T, 3 times 45W, and so on and so forth. But by setting it up like this, sometimes these will have many things that follow after this. And it's easy to see. If you don't set it up like this, then you're gonna run into problems later. Okay? So let's look at this problem here. Hydrogen sulfide, a foul-smelling gas, is found in nature in volcanic areas. The chemical reaction for the burning of hydrogen sulfide is given below. Balance the equation and interpret. So first we have to balance our equation. And it appears to be, no, it's not balanced. I thought it was balanced for a moment. Okay, now I believe it's balanced. We have 4 hydrogens on this side. We have 2 sulfurs, and we have 6 oxygen. And over here we have 2 sulfurs, 4 oxygen, plus these 2 oxygens, so 6 oxygen and 4 hydrogen. So you can see that they're conserved. The atoms are conserved on both types, on both sides of the equation. And so that's the number of representative particles, what I've just written here. 4 hydrogens, 2 sulfurs, and 6 oxygens are the number of representative particles. And it's saying representative because that is technically, like I said over here on the previous slide, that is technically all multiplied times, well, I deleted it. That's technically all multiplied times 6.022 times 10 to the 23rd, right? Each of these numbers, these coefficients, are multiplied by 6.022 times 10 to the 23rd to have the true number of atoms. So that's why it's called representative particles, okay? So the number of moles, the moles are represented by the coefficients. So we have 2 moles of H2S. We have 3 moles of O2, 2 moles of SO2, and 2 moles of H2O, okay? The volume of the gases, all right? Remember, 1 mole of each gas is 22.4 liters. So we have 22.4 times 2 for the hydrogen sulfide. So that would be 22.4 times 2 is going to be 0.8 liters of H2S. We'll have 22.4 times 3, so 67.2 liters of O2. We'll have 22.4 times 2, so 44.8 liters of SO2. And the last one will also be 44.8 liters of H2O, water vapor, or gas, okay? And that's the volumes of those gases, all right? So if we look at the masses of the reactant and the products, sulfur is 32, hydrogen is 1, so plus 2 is 34, and then we have to multiply by this coefficient. So 34 times 2 is 68, so we have 68 grams for the first one. Oxygen is 16, and we have O2, so that's 32, times 3, so would be 96 grams for the 3O2. And then sulfur dioxide is going to be 32 for the sulfur, plus 16 for the two oxides, so that's 64 times 2 is going to be 128 grams, okay? And then each water is 18, and there's 2 of those, so that would be 36 grams. And if I've done this correctly, 128 plus 36 is equal to 164. 68 plus 96 is also equal to 164. Okay, and so you can see there again that mass is conserved. Okay, we're going to skip over this since we're not in class to do the demo. I don't know if that's in your notes there or not, but if it is, you can just cross through it. So I want you to try this one. Balance the equation, interpret the equation in numbers of molecules and moles, and then show that the balanced equation obeys the law of conservation of mass. You push pause and I'm going to work this, and then we'll come back together and you can check it with me. So when we work out this problem here, interpret the equation in terms of numbers. Well, first we had to balance the equation. So if you put a 3 in front of O2, 2 in front of CO2, and 3 in front of H2O, then that will balance the equation. Now, I suspect that some of you may have put a 2 here, a 6 here, a 4 here, and a 6 here. And honestly, I did that the very first time that I balanced it. But if you see, that can simplify down if you divide all of them by 2 into 1, 3, 2, 3 for the coefficients. So always make sure your equation is simplified. You'll get the same thing either way, but it's just nice to have it simplified. And then interpret the equation in terms of moles and molecules. So again, the moles are just the coefficients, 1, 3, 2, 3. And so that's what I put here, 1 mole of C2H5OH, 3 moles of O2, 2 moles of CO2, and 3 moles of H2O, okay? And then the molecules, you multiply the number of moles times 6.022 times 10 to the 23rd. So we have 6.022 times 10 to the 23rd, since there was just 1 mole. We did 3 times 6.022 times 10 to the 23rd. So that made 18.066 times 10 to the 23rd molecules of O2. And then also down here for the H2O, okay? And then for the CO2, there was 2, so that made that 12.044 times 10 to the 23rd molecules there. So that checks off the first one. And then show the balanced equation obeys the law of conservation of mass. So I calculated the mass for each of the parts, okay? And then when you add those up, 46 and 96 makes 142, and then 88 and 54 also makes 132, and those are equal, and so that obeys the law of conservation of mass, okay? So your assignment for today, you have a couple of these to try. You have this page, Interpreting Equations, and I will say this is very likely stapled to the back of your stoichiometry notes assignment. I think it just got stuck there, so check there for it if you can't seem to find it. And then on the back, you have some dimensional analysis practice. So like I said, stoichiometry is a lot of dimensional analysis type stuff, so I'm going to have you practice that skill here. So for the first one, we always start with what they've given us. So they've given us 38.5 liters, and we are trying to get that to milliliters. We know that we're going to want liter on the bottom, and I know that 1 liter is 1,000 milliliters, so I can cross my units out, and that should leave me I think that would be a dot there. 38,500 liters. Okay, or you can leave that extra zero off. 38,500 liters. Okay, so that's what you're going to do on those 7 problems. On these first 4 problems, it's kind of like what we just did. You're going to calculate the molecules, the moles, and the volumes of the gases. So remember, 1 mole of a gas is 22.4 liters, and then 1 mole is equal to 6.022 times 10 to the 23rd molecules, or particles, or atoms, if it asks you for any of those. Okay, now here it says representative atoms. You can write it like this, that's fine, or you can also write it how you would balance the equation. Like you would say there's representative, there's 2 potassium atoms on each side, and that would be okay for that. I'll take it either way that you do it. Okay, so not too much to do today. 11 problems. It should be pretty quick and easy. Let me know if y'all have any questions on it, and y'all have a good day.